Right, today we are going to talk about the Laplace transform, and we will finish that in this week. Okay, so, and actually we just talked about this two weeks ago, but let's see that again. Actually, what is the Laplace transform? For the Laplace transform, let's review. Actually, we learned that in the first half of this semester, if I have an eigenfunction and send it to the LTI system, so this is eigenfunction, and what is h over s? Whatever you have for the exponential, you have the same and plus and times this coefficient, that's the eigenvalue, right? So this is an eigenfunction. And then the HS, the transfer function, it is the eigenvalue. Okay, and then for the Laplace transform, we also done the Fourier transform. So the difference actually, the Laplace transform is a generalization of Fourier transform, because in Fourier transform we focus on the imaginary axis, but we extend it to all the plane. That is the Laplace transform. Okay, so here we see that actually when we do the Laplace transform, it is the x the signal times the exponential. We do the Fourier transform of this term. So we will see here is sigma. And this is j omega, and here is your x. Just sigma plus j omega. In the past, in Fourier transform, we just talk about this j omega, but now we can extend it to here. We may have a waveform here. Okay. Let me see. All right. So we know for the Laplace transform, it is 1 over 2 pi suppose, let's just have sigma plus j omega. Okay, e to the sigma plus j omega t omega. And then to get x sigma plus j omega, or say sigma 1. It is x times e to the minus sigma 1 plus j omega t dt. Remember that when we say that in Fourier transform, how do we get the coefficient? your signal in the product your basis. Right, and because it's the function in the product, so you have the conjugate. But in this case, this is this the basis? We have e to the sigma 1 plus j omega t. If I take the conjugate, what do we have? Still e to the sigma 1 t. And here we have minus j omega t. We only have minus this part. Okay, so if I have the a signal in the product, their basis here is different. So this is not the basis. Okay, I have minus sigma 1 t. So here we know that this is not the basis. But we say that Laplace transform is the generalization of the Fourier transform. So if I get rid of e to the sigma 1 t, so put it on the left hand side, xt times e to the minus sigma 1 t. This is 1 over 2 pi x sigma 1 plus j omega times e to the j omega t d omega. In this case, this term, now it is a basis, which means that to get the coefficient x sigma 1 plus j omega, then there will be your signal in the product, the basis. So your signal is x times e to the minus sigma 1 t times the basis, and here we need the conjugation, so minus j omega t. Now, so far, first we learned Fourier series, continuous time, and discrete time. Now we extend to our main part, that's the Fourier transform, continuous time Fourier transform. Okay, they extended to continuous time Fourier transform. For the discrete Fourier series, then we can extend it to discrete time Fourier transform. Okay, now for this continuous time Fourier transform, we will extend it to the Laplace transform. Next, like last week, next week, the discrete time Fourier transform, I can also extend it to what? The Z transform. Okay, so here you can see that for overall this course, this semester, we done the Fourier transform. For this Fourier transform, they can extend it to continuous time Fourier transform. I can extend it to Laplace transform. I only focus on the frequency, then we use the Fourier transform. But I want to see more, then we use Laplace transform. Today we will see that why we use Laplace transform, because we can see more system properties or something on that system. We will see more because it extended to the whole plan. not just in the imaginary axis. Similarly, for discrete time signal, the Fourier transform, I can extend it to the Z transform next week. Okay? And then we have some examples. It shows that I have this signal, and this signal, I only have a value when t is greater than 0. This signal, we can also say this is a right side signal. The right sided signal. And the other one, I only have a values when t is less than 0. So this is the left-sided signal. So here is left-sided. Okay. For the right-sided signal, I found the Laplace transform 1 over alpha plus s. Left-sided signal, I also found the Laplace transform 1 over alpha plus s. They are the same. However, the difference is the ROC, the region of convergence. The region of convergence is different. For the right-sided signal, okay, the convergence is like to the right side. For the left-sided, to the left side. So now you know that for the Laplace transform, if you want to find the Laplace transform, this is not the only result. You also need to tell me the region of convergence, because different regions of convergence may give you a different signal. Okay. In the past, here which I should write down, this is the magnitude of x sigma plus j omega. In Fourier transform, we only focus on the value at the imaginary axis. But if I plus like sigma 1, so extend it to here, this is also the Fourier transform, but the Fourier transform of x times the exponential. Okay, and why this is the magnitude? Remember that for the Fourier transform, well, we have magnitude and also the phase. Okay, but phase is hard to plot. You can see that it should be the first one and second one. I have an angle. I have an angle, and here, and maybe go down, and this is going down, going down. Okay. How to plot? So we just plot magnitude. Okay. Remember that this is a person. Okay. So the easier way is that let me let's have 5 people. Easier that let me have 5 people here. Maybe that those group, please stand here. Yes, stand here. So now you can see that the magnitude is just like, now you just face your students. Okay, if you want to find the magnitude, it's just face to the students, right? But you remember that for the complex signals, they have the angle, which means that maybe the first one is here, but the second one they face in that way. The third one they maybe face here. Okay, and the next one they will face opposite to you, and also in the other way. So you can see that if I really want to plot the phase, how to plot that in the paper, right? But you still need to remember that for the Fourier transform, because of different phase, they were toward to different angle. Okay, and that's why like for that unit circle that you just turn that 2 pi, then you go back to your original position. Okay, so thank you, go back. So here we only just plot the magnitude. And for this one, you can see that, again, the complex exponential, they are omega 1 and omega 2. They are bases. But if I shift that to here, a plus sigma 1, delta sigma 1, then they are not orthogonal. This one and this one is they are not orthogonal, so they are not the basis. So for overall this plan, we only have a basis here. Okay, we won't have extra bases. And so here's a note: Laplace transform is a generalization of the Fourier transform. And for this X, Laplace transform may not be well defined, because if it is not convergent, then it is not defined. But we may cover more signals, and we can also analyze it. For example, like for the Laplace transform, we can have the Laplace transform as the numerator divided by denominator. So here, to get the root, you have zeros. And here in the denominator, you have poles. So later on, we can have a pole 0 plot, which the Fourier transform cannot do it. And also that for the Laplace transform, okay, it may converge at some region in the S-plane, but they cannot do it in Fourier transform. So we will see more examples today. And since you see that for the previous examples, I may have the same Laplace transform, but with different regions of convergence. So let's see the properties of region of convergence. So first, the Laplace transform may consist of vertical strips in the complex plane. Why the region of convergence consists of vertical strips? So here, the region of convergence of X consists of those S equals sigma plus that'll be alpha plus J beta which the Fourier transform of X times e to the minus alpha t still have converges this condition go back. Depends on alpha, not beta. So it really depends on this part. Okay, if we take the integration, we care about this part, depend on alpha, and then I think we have a proof. You have a proof later. Okay, so for the region of convergence of a Laplace transform, it's the vertical strips. So if this point converges, this whole line converges. Okay, if this point, maybe here, this point converges, this whole line converges. So we may have, it could be here, they all converges. Or they converges for the whole plan. So it could be the entire plan. The second one, the region of a convergence do not include any poles, because in poles, the poles means that this is 0. Then overall, there's divergence. Okay, so I cannot include any poles. Poles means that in the denominator, which makes the equation 0 in the denominator. So overall, this fraction goes to infinity. So cannot include poles. And then next one, if the signal is finite duration means that I have a Tm. If t is greater than Tm, the absolute t, the signal is 0. In this case, the region of convergence is the entire complex plan. Because and here is the finite duration. After Tm, before Tm, minus Tm, they're all 0. I only have a values between minus Tm to Tm. Because the Laplace transform when I do the Laplace transform, I only have a values from minus Tm to Tm. These may converge as long as the signal is bounded. The signal is bounded, then it converges. So they will converges so long as the x is bounded. So that's why that the region of convergence is entire S-plan. And here I would like to add if the signal finite duration and also absolutely integrable. Integrable. Let's see why. So I need to take the magnitude, which means let's see if it is bounded. Again, I have values only when t is between minus tm to tm. Okay, I can put the absolute value inside. So inside this one will be less than. I take the absolute value first and then do the integration. So x times e to the minus st dt. Okay, this means I have absolute value of x, this signal, and also the absolute value of e to the minus st. Which means what is the absolute value of e to the minus st? It will be e to the minus alpha t. Okay? Why? What is e to the minus st? S is we use sigma plus j omega, right? Yeah, we use sigma plus j omega. So the absolute value of e to the minus st is equal to e to the minus sigma t. I need to check. Yeah, we use sigma, and also e to the minus j omega t. Okay, so here we need to change that to sigma. Okay, because absolute value of the complex exponential, that's 1. So if x is bounded, then we say that this is less than b times the integration. Okay, if it is bounded, so it really depends on alpha, sigma. Because we say x bounded means there exists b such that x magnitude is less than b or less than infinity. Alright, so the region of convergence will be either right-sided, left-sided, or entire plane, or both-sided. Okay. Right-sided, for example, we got this example, and also left-sided, or even the entire plane, if I have a finite duration signals, or both-sided. We will see this in a minute. So for example, if I have this signal, this is right-sided, right? This is left-sided. So what is the region of convergence? I need to find the intersection for this. For example, let's write here. The Laplace transform, if I take the Laplace transform, first, e to the minus t ut minus Laplace transform e to the minus 2t u, the unit step. Okay, first, what is the region of convergence? Check here. There'll be 1 over alpha plus s, and then it should be greater than minus alpha, right? So here, greater than minus alpha, alpha is 1. So this should be greater than minus 1. For this part, region of convergence is less than 2. So the Laplace transform is 1 over s plus 1 minus 1 over s minus 2. So for this, the region of convergence should be the intersection intersect the region of too big. Should be less than 2. So if we plot this, here's minus 1, and here's 2. Minus 1 and 2. Let me try if I use. Oh, okay. Let's see. 8 red. So greater than minus 1, less than 2. The intersection is in between. So we have this region. There will be the region of convergence. Now, if the signal is left-sided, okay, left-sided means that after Tm is 0, but before that I have values. Then the region of convergence is the half plane to the left of some vertical line. That means this is some vertical line, and then the region of convergence is here. If it is right-sided, this is right-sided. Before Tm is 0. After that, I have values. Then the region of convergence is the half plane to the right. If it is two-sided, what does that mean, two-sided? Two-sided means that x is infinite duration. So there's no like Tm to get that x is, the value is 0. For t is less than Tm or t is greater than Tm. If x is two-sided, then the region of convergence is a vertical strip, like for example, like here. We can also think about this as oh, by the way, for the region of convergence may not exist. It could be the entire plane, a strip, or left or right. You can think of the signal. The signal could be the right-sided signal plus left-sided signal. So this is a right-sided. And here is left-sided. I want to find the region of convergence, so I want to find the intersection of these two. So once the intersection, there's no intersection, then we don't have a region of convergence. The region of convergence is the region of convergence of the right-sided signal intersect left-sided signal. If my Laplace transform, if the Laplace transform can be expressed as rational, okay, we know we just mentioned that we have zeros, and also we have zeros and also poles. Then the region of convergence is bounded by poles, because the region of convergence cannot include poles. So we will never include the poles. never will never include the poles. So in this case, suppose X is right-sided, then what is the region of convergence? They say it is the half plane to the right of the rightmost pole, which means the pole with largest real component we learned that for the right-sided, okay, it is the vertical and to the right, the half plane, okay. But if I have a poles, so suppose I have poles and here, poles in conjugate pair and here. And where is the region of convergence? The half plane to the right of the rightmost pole. Which one is the rightmost pole? This, the rightmost pole to the right. So here, to the right. Okay. Similarly, for the left-sided signal, if I have a poles here, then the half plane to the left of the leftmost pole. In this case, leftmost pole is this two. So here is the region of convergence. That also means the pole with smallest real component. And then later on we will see an example. Alright, let's continue. So here's the example. Alright, my Laplace transform is here. But I want to find the signal. Remember that for Laplace transform, even though I give you this answer, that's not enough, right? Different region of convergence will affect your signal. Okay, so in this case, if my region of convergence is greater than -1, then what is x? Oh, you can try it. Yeah, let's try. Let me see. You can try it by yourself first. Okay. Normally for Laplace transform, I have a rational. We need to do the partial fraction expansion. So far, we only know what? This. If I have e to the minus alpha t, times unit step function, then we have 1 over s plus alpha. Okay, so here we can do the fraction expansion to make the Laplace transform as 1 over s plus something, or 1 over s minus something. Then we know that it is e to the minus alpha t ut. Okay, so first let's do the fraction. One over s squared plus 3s plus 2. What's the fraction? If this will be s plus 1 and s plus 2, right? We get 1 and minus 1. Okay, so now we need to consider the region of convergence, this greater than minus 1. So first we can plot a, let's say A, we have minus 1 and minus 2. Let's have minus 1, minus 2. So we can copy. So first, x, it should be greater than minus 1. So here, if it is greater than minus 1, we do the intersection, right? For intersection, this one is greater than minus 1. This one, if I do the intersection, is greater than minus 1. Then here, it is also greater than minus 2. So the intersection is here, which means that the signal is, well, both signals here are right-sided. Okay? X is e to the minus t ut and minus e to the minus 2t ut. So they are both right-sided signal. Okay. This is the overall, right? The overall, we say that the region of convergence should be greater than minus 1. S should be greater than minus 1. We know that this S should be greater than minus 1, and this part, we need this these two to intersect. Both should be greater than minus 1. That means this should be greater than minus 2. Correct? So overall, the intersection is that the S should be greater than minus 1. The second one, this should be less than -2. So it's in this region. Can you figure out what is the signal? Overall, it should be less than -2. But we have these two signals. Right, what is x here? And this one. The intersection, finally, there will be still less than -2. How can I get the region of convergence left-sided? Check your note, right? When can we get this? Minus sign. I also have u to the minus t because it is a left-sided signal. I only have the values when t is less than 0. Okay? So minus e to the minus t, but here u will be minus t. Okay, here u is the reverse of the unit step function. And how about this one? I have values between, the region of convergence is between -1 and -2. All right, any questions for this one? In between, so that means for -2, it's right-sided. For -1, it's left-sided. So the intersection is in between. Right, next. If I have a higher order of the denominator, like this one, and x is both-sided. What is, now we just said x is both-sided. What is the region of convergence? So here we see that the pole is -1, 1, and -3. So here we have 1, -1, and -3. So 1, -1, and -3. Okay, so x is both-sided. So the region of convergence could be here. Pole is not included. Or between -1 and 1. Alright, now let's see the properties of the Laplace transform. Okay, so after learning the regions of convergence, let's see what are some good properties of Laplace transform. Signal x, and then I have a Laplace transform x of s, region of convergence are x1, Laplace transform x1, region of convergence R1, and also same thing for for x2. First, linearity. Okay, actually you also learned Laplace transform before, right? In your second year, so this should be not that hard. Linearity, just like a Fourier transform. If you do the linear combination of your signal and you take the Laplace transform, the Laplace transform is also like the linear combination. And then, but this is not the final result. We also need to care about the region of convergence. Here, the region of convergence definitely the intersection of your R1 and R2. But here we have the soup. I mean, the region of convergence could be more than the intersection. Why? It should be like equal to the intersection, but sometimes it could be more than that, because when we have the pole zero cancellation, then the region of convergence may be bigger. If pole zero cancellation. The second one, the time shift. If I shift in time domain, in your S domain, same thing, that the magnitude is still the same. They only have the difference with the phase. And the region of convergence is still the same. Okay. We can see why. Okay, now I have alpha. I should change to sigma. So what is the Fourier transform of x of alpha plus j omega? That's a signal times e to the minus alpha t. Right. So now let's see, if I shift by t naught, and then do the Fourier transform, this I would change the variable. T becomes t minus t naught. Okay, if t becomes t minus t naught, then we have the integration x t minus t naught, and I need minus alpha. T becomes t minus t naught. And then e to the minus j omega, t becomes t minus t naught. Since I time e to the alpha t naught, and also here e to the j omega t naught. So overall, this I should times the inverse minus minus in front. So in front, I have e to the minus alpha plus j omega t to compensate. So we have e to the minus alpha plus j omega t naught. This should be t naught. This one, this is the Fourier transform or Laplace transform for let's see, x of s, and we say s is alpha plus j omega, or you can think of e to the minus st naught x of s, and that s is alpha plus j omega. Similarly, that we can also shift in S domain. If I shift in S domain, for Fourier transform, it's like doing the modulation, right? Here, similarly, if I shift by S naught, that means in time domain at times e to the S naught t. And then the region of convergence, the original one, and also plus the shift. Okay, this means S plus this is just that the region of convergence shift by S naught. So here's the example. In S domain, I shift by 1 plus j, which means the region of convergence is the original region of convergence shifted by 1. So shift 1 to right. Corresponding the time signal. E to the 1 plus j t x t. Suppose the x naught is just the imaginary value j omega naught. Okay, there's no like real part. Then if I shift by j omega naught in time domain, I also do the modulation. Here's e to the j omega naught t. And then the region of convergence is just shift along the imaginary axis. For example, this is the real part and the imaginary part. I want to plot the magnitude, just the magnitude of the Laplace transform. So here is x omega, the magnitude, and the shift by omega naught. So I shift that to here. And here you will see this will be the pole. Here will be the pole. And I shift it to pole here. All right. Next, time scaling. We do a compression or expansion. So if I do the here we can say compression or expansion. So if I times a could be greater than 0, greater than 1, or less than 1. Okay, so the region of convergence, in the past that's R, and here we have AR. Okay. For example, if my Laplace transform with the region of convergence is this. Okay, suppose it is 1 here. Okay, and it is to the right. Now, if we have a equals minus 2, so x of minus 2t, this Laplace transform, that'll be 1/2 times x s over minus 2. So I reverse. So in this case, my region of convergence is at minus 2 alright, to the right or to the left, here or here. Should be left hand side. And here we have a special case if a is just minus 1. Okay, if a is minus 1, then the regional convergence is here minus s. Minus s means the original ROC just flipped over imaginary axis. Next, conjugation. So for conjugation, if I conjugate in time, in S domain, I also conjugate both. Conjugate your Laplace transform and also S conjugate. The region of convergence is still the same. So what is the conjugation here? This is the real part, and here's the imaginary part. A S. So if this is S naught, then the conjugation here, symmetric by the real axis. Here's the theta. So the Laplace transform will becomes your original Laplace transform but conjugate, and S naught also conjugate. But when the signal is a real signal, the conjugation is still the same. Okay, so here this equation holds, because when x is real, that means the conjugation of the x is still x. Then when I take the Laplace transform, here's the Laplace transform, and this Laplace transform is x conjugate s conjugate. Here also tells us that for the real signal, if we have a complex poles, then this pole, the poles will appear or will occur at conjugate pair. Okay, if I have a poles here, you can expect I also have a conjugate pole, this one. I cannot just have this one alone. If it is in the real line, that's okay. But if it is in the complex plane, I also have a pair. So, for this example, can you identify or indicate the poles and zeros? So suppose here we have 1, 2, 3, minus 1, minus 2, minus 3. 1, 2, minus 1, minus 2. Okay, this is 3, minus 3, 1, 2, minus 1, minus 2. First, we have a poles. We have a zeros. 0 is minus 1. So here I should have minus 1. Okay. And then the poles 2 plus 3j here, and minus 2 minus 3j here. So this is the pair. Next, the convolution in time domain. In Laplace domain, it is the multiplication, and the region of convergence will be the intersection of R1 and R2. But here again, it should be equal or even greater than that. Why? When I do the convolution, when I do the multiplication, we have zeros and poles, zeros and poles. Maybe something that cancel out. When they cancel it, the region of convergence should be bigger than the intersection. So, so here, if I have a pole zero cancellation, then the region of convergence may be larger. So if I send it to the LTI system, X and the LTI system H, then your output is Y, that is X convolved H. When you take the Laplace transform, here is the multiplication. Next, let's see the differentiation in time domain. If I take the derivative in time domain, then similarly that in S domain I generate S. Remember, for the Fourier transform I generate J omega. Okay, here I generate S. And then the region of convergence could be greater than the original one, because at times s, see, at times s, if the denominator has s, then I cancel out. Okay, so if a pole at s equals 0 cancelled, then my region of convergence become larger. And then for the S domain, if I take the differentiation in S domain, in time domain I times t, each time I times t. And the region of convergence is still the same. For integration, if I have an integration in time domain, then I have 1 over s. So again, 1 over s, I have zeros and poles. Maybe they will cancel it. So my region of convergence could be bigger. For this one, 1 over s. What is 1 over s actually? We have x over s, that's r, right? The region of convergence is r. But what is 1 over s? In time domain, which signal has the Laplace transform 1 over s? The unit step function. Okay, the unit step function. So the unit step function, then the region of convergence is like greater than 0. And also, why is 1 over s times Laplace transform? See this integration. This integration, you can think about the signal convolved unit step function. Okay, and then the unit step function, the Laplace transform is 1 over s. And then the region of convergence is greater than 0. And we also have the initial value theorem and the final value theorem. Okay. X is 0 when t is 0. The signal is causal. So this is a causal signal. For the causal signal, and I may have the singularities at 0. So for the initial value theorem, at 0, that means I take the limit s times the Laplace transform. S goes to infinity. For the final value theorem, s goes to 0. Okay, in this time, s goes to 0, then that means in time domain that the t goes to infinity. Any questions so far? Right, next now we can see that why do we learn Laplace transform? Okay, we need to apply Laplace transform to our linear time invariant system. Right, so let's see. With a Laplace transform, we need to think about two things, the causality and stability. With a system, a causal system has the transfer function h over s. The region of convergence is a right half plane. Okay. We can also plot for the unit step function, the region of convergence is here is 0. And then, what does that mean, right half plane? this means that the H is right-sided. So if I have a system with a rational H, the transfer function, causality means the region of convergence being the right half plane to right of the rightmost pole. And I still miss the period. Okay. So right-sided means the H okay, suppose it's O0 and then have a value to 0. Here we have a conclusion that if it is causal, that means it is right-sided. And right-sided means that the region of convergence is right half plane. And then the other way around, if the region of convergence is right half plane, that means it is right-sided. Right. And how about here? The right-sided, that means the signal or system is causal. Correct? So that also means that right-sided, that means causal. Is that correct? If I say that it is a right-sided signal, then it is also causal. Here's the example right-sided, right? Why it is not correct? What is a right-sided signal? If my right-side signal like this one, this is 0. Here's TM. This is right-sided, right? But before 0, I still have value, so it is not causal. Okay? Right, next about the stability. We say the system is stable when, if and only if the region of convergence of the transfer function that will include the imaginary axis. Okay, and the H should be absolutely integrable, or the Fourier transform converges. Then we say the system is stable. Okay. So as long as you have, this is the J omega, your region of convergence include the J omega axis, then the system is stable. And we say that a causal system with a rational H, which means we have zeros and the poles here. We say this is stable if and only if all poles lie in the left half of S-plane. So all the poles should be in the left half of this S-plane. If I have a pole here, then it is not stable. Okay. And then the region of convergence is the right to the rightmost pole. Here, let's see some examples. If this is the axis, I have poles I want to have the system to be stable. Where should I have our region of convergence? First, I need to include the j omega axis. And then the region of convergence is to the right of the rightmost pole. The rightmost pole is here. So here is the region of convergence. In this case, the system is bounded if the system is stable. The region of convergence should include the j omega axis, and the system is causal. That means the region of convergence is the right half plane. Okay, so I'll give you 3 examples, and you need to tell me that if the system is causal or stable. If first, here's the real part, imaginary part. I have poles at 2, 1. I have zeros at 0 and poles at -1. So if my region of convergence is here, right, the system is causal, stable, or non-causal, non-stable. This system is causal or not, stable or not. First, is it causal? Is it stable? Okay, so this is say the system is causal because the region of convergence is to the right half plane, and unstable because I don't include the j omega axis. The second one, I have a poles at -1. 1 I have zeros, and 2 I have poles. And here's my region of convergence. So in this case, is it causal, stable, or not? Stable or non-stable? Unstable or causal or non-causal? First, let's check the causality. Is it causal? no, because we need the right half plane. Okay. How about stability? Is it stable or not? Why it is stable? Yeah, because it includes the axis. Once they include this, it's stable. So it is non-causal but stable. Last one. If I have 2 as a pole, 1 as a 0, -1 as a pole, and my region of convergence is here. And how about this one? This is unstable, right? And we call this anti-causal. So what is anti-causal? We have values. We don't have values when t is greater than 0, and then the region of convergence is the left half plane. Okay, so the h will be like when t is greater than 0, that's 0, and I have a values when t is less than 0. Next one. If I have a signal, okay, the signal is e to the minus b times absolute value of t. So in this case, we can rewrite this signal using the unit step function. So for both signals here, this is right-sided signals, right? So the region of convergence should be greater than minus b. And for this part, this is the left-sided signal. Okay, so the region of convergence should be less than b. So if I combine these two here, the region of convergence is between minus b, and b is greater than 0. Okay. Here, let's see. When b is greater than 0, this signal looks like this is 1. So when b is greater than 0. When b is less than 0, then the signal looks like and then the region of convergence, it's too close. For b greater than 0, we have b and minus b. It's in between. But how about b less than 0? What is the region of convergence? Well, actually, we don't have Laplace transform. Next, let's see how do we use the Laplace transform to analyze the system. So if I just know that I have an input and output, and I have the input to the LTI system, this is our input, and I got the output. I only know the input and the output. Okay, and I know that it's the LTI system. So I want to determine the system function. Right, so in this case, first we can take the Laplace transform. If I take the Laplace transform, the input is 1 over s plus 3, and then the region of convergence is greater than 3 or minus 3. For the output, s plus 1 times s plus 2. Okay, the region of convergence is s greater than minus 1, or maybe write it down, ROC. So what is h? We know the system function, that should be the output divided by input, and this gives us s plus 3 divided by s plus 1 times s plus 2. What is the region of convergence? Same as y? Why? Any reason that you can explain? Remember the property convolution? Okay. In S-plane we have a multiplication. Then what is the region of convergence? The intersection, right? The intersection of these two will be the region of convergence for y. So for this intersect, this one still be s greater than minus 1. So here, this is minus 3, right? So I have a minus 3, greater than minus 3. And then what is this? To get the result, the intersection is the s is greater than minus 1. Then the region of convergence is greater than minus 1, right? Because the region of convergence of y should be the region of convergence x intersect region of convergence h. And for h, we have pole at s equals minus 1 and minus 2. So now you found the system, the LTI system. Here's the region of convergence. So in this case, let me ask you the causality and stability. Is the system causal, stable, or no? Okay, first it is stable, right? Because this is j omega. We include that. So the system is stable. And this is the region of convergence, right? It is the to the right of the rightmost pole. This is, we have -1 and -2. This is -2, this is -1. So here, and we have right half plane. So the region of convergence of the system is to the right of the rightmost pole so in this case the system is causal. And also the second one, all poles in the left, so first, second, left half plane so the system is stable. This is for the Laplace transform. Next week we are going to talk about Z transform. That is the extension of the discrete time Fourier transform. Okay. But before this, let's talk about the perfect reconstruction. Okay, here is the perfect reconstruction. Next week, you will see that next week. But we can talk about this first. So you can take a picture. So what is the perfect reconstruction? Like we sample the signal, and actually we try to have a reconstruction perfectly. How do we make sure that we can do it? So suppose we have an analog signal and we have the bandwidth. The bandwidth is 40 radians per second. The sampling rate is 100. So with this condition, do we have aliasing? No, because greater than the Nyquist rate, right? Okay, there's no aliasing. Okay, and then my signal, okay, the discrete signal here. So what is the perfect reconstruction? The perfect reconstruction will be your discrete signal times this h, and then the h looks like that one. Okay, I need to determine to find a simple closed form for the reconstructed signal. How can we rewrite the simple and closed form? First, we need to check if I have a sampling rate 100, that means Ts is 2 pi over omega s. That's 2 pi over 100. Okay, so we need 3 criteria. First, it's definitely that we don't want to have any aliasing. So is the sampling rate greater than the Nyquist rate? Second, is this H kind of like a filter such that the Fourier transform is 0 for where? when the sampling rate minus the bandwidth, if the frequency is greater than the difference of your sampling rate and the bandwidth, is that 0? Because we want to make sure that we can fill out any rapid cuts. So this is necessary to filter out all the rapid cut. And then is this filter the height or in your frequency domain is Ts. Because I need to times Ts back so I can have the same magnitude back to the time domain. So this ensures the original Fourier transform centered at omega equals 0 is passed unaltered. If we can meet those three criteria, if these three criteria are met, then our reconstructed signal can be expressed, this should be T. Should be the same as our original input that is sampled at T over Ts. Okay, so for our example, the sampling rate is 100, bandwidth is 40. So 100 is greater than 2 times 40, the Nyquist rate. So there's no aliasing. Now let's see the H, the filter. The filter in frequency domain. Now in time domain, now you see that I have a sinc function times together. In frequency domain, I have sinc function rectangular, convolved rectangular. They have a different width, so it is not the triangle. You finally, after convolution, you'll get the trapezoid. Right? So here 50 plus 10 will be 60 minus 60, and here there'll be 40 minus 40. Okay? So So if you plot the filter in frequency domain, you will get so here we have 60 minus 60, 40 minus 40, and then the height is TS. So you can also check that actually the criteria 2 and 3 are met. So you can write the reconstructed signal in a closed form. Okay, so we sample that T over Ts, which is 100 times T over 2 pi, which is 50 T over pi. So you bring this here. So the n becomes 50t over pi. You get pi over 5 sine pi over 10 times 50 over pi t divided by pi t, and sine 3 pi over 10 times 50 over pi times t divided by pi t, 2j sine 2 pi over 5 50 over pi t. So here's your closed form, simple closed form, pi over 5 sine 5t over pi t, and sine 15t over pi t times 2j sine 20t. Right, any questions about this example, the perfect reconstruction? First, what is the Z transform? Again, remember that we have Fourier transform, right? For the Fourier transform, the extension is Laplace transform. And then before Fourier transform, we done Fourier series. We have a continuous time Fourier series and discrete time Fourier series. So continuous time Fourier series, we extend that to Fourier transform. Discrete time Fourier series, we extend that to discrete time Fourier transform. And now the discrete time Fourier transform, I can have extension to the Z transform. The Z transform is the generalization of the discrete time Fourier transform. And for the Z transform, actually, if you learn Laplace transform well, you just apply everything to Z transform. It's parallel. It's quite similar. So once you know the Laplace transform, you just change that to discrete case, then there'll be a Z transform. Okay. So the Z transform is the extension of discrete time Fourier transform. But in this case, because it is an extension, so they will cover more class of signals. So we can find more details about Z transform. So in the Z transform, it is on the complex sinusoidal representation of the discrete time signal. Remember, for the LTI system, okay, for LTI system, I sent Z to the n, or e to the j omega n. That's the complex exponential. What is the output? This is like an eigenfunction. Okay, so I have a Z to the n, e to the j omega n. And then eigenvalues. Here the eigenvalue is z, h of z. And this h of z is just the Z transform. Okay. Any questions for this? For the Laplace transform, we extend the imaginary axis to the whole S-plane because we have the sigma, the real part. How about the Z transform? For the Z transform, well, because if I plot, then we can plot that next week. We will consider the unit circle. Here is the unit circle. This is the real part and imaginary part. Laplace transform, here is the real part, imaginary part. But now we will focus on this unit circle. Okay. We will talk more about this next week. All right, any questions for this?